There are many situations where a sphere traveling through the air spins. But let's face it, the most interesting ones are balls, like sports balls. In this podcast, we're looking at how different spin rates and roughnesses affect a ball's aerodynamics, and as we'll see, the results are a little surprising. So figure 2, we see the general flow pattern around a quite smooth ball that is spinning. There are a few important general points though. The first one is that there are blue and red little bits. These are effectively the wake behind the ball. So for this one, the wake isn't quite as wide as the ball itself, but it's not far off. You can see it's almost about the same. That brings us to the size of the ball. So in this picture, we have the top and bottom, which are the sides of the ball here, and they are with low pressure regions. It says here, low pressure, low pressure. The flow separates fairly smoothly after those low pressure regions. Then at the front, we have high pressure, and at the back, we have low pressure. Or not quite low pressure, but somewhere in between the low and high pressure. It's lower than the front, and that's important because that creates drag. But anyway, what does all of that mean? So the greater the difference in pressure between one side and the other, so for example the front and the back, that means we have more drag, or top and bottom, that means more lift. And from a practical point of view, the more drag, for example, a ball has, the quicker it will decelerate, so the speed will drop sooner. For sports balls, that could be a good thing or a bad thing. So for example, a baseball, if a ball's speed changes quicker, that will make it potentially harder to hit. On the other hand, if the ball can remain fast, then it could make it harder to hit if the ball was already fast to begin with. But in addition to that, if the ball remains faster, then other aerodynamic properties also become more severe. And that leads us to our next point. So as we mentioned, there's low pressure on top and underneath the ball. And if there's a pressure difference between the two, then the overall force on the ball will be either up or down, if there's an asymmetry here. And if there's higher pressure underneath than on top, that will create a lift. If we have higher pressure on top compared to underneath, that produces downforce. And coming back to an example like a baseball, if you can produce lift or downforce on the baseball, then that will make it rise or drop more than expected, and that'll make it harder for the hitter to hit. And things get even more interesting when you factor in the drag here. So remember when I said that if the drag is high, then the ball will decelerate quicker. That is important because all these aerodynamic forces like the drag, lift, and even side forces are proportional to the velocity of the ball compared to the surrounding air squared. What that means is that if you increase the speed of the ball, the forces on the ball will increase too, but the important thing is that the forces won't increase by the same amount that the velocity increased. Instead, they'll increase at a faster rate. In fact, if you double the speed, the forces will then increase by a factor of 4. What that means for this ball is that if the drag on the ball is high, that will drop the speed of the ball quicker, and that will reduce the lift on the ball even more because the lift is proportional to the velocity squared as well. It'll also drop the side force as well. So that explanation was a little bit complicated, but the takeaway here is if the drag on the ball is high, it might decelerate the ball faster, which then makes it harder to hit. But if the lift and side forces drop as well, then that will also make the ball less hard to hit. And if you have the side forces higher, so you can hit the ball faster, that might make the ball harder to hit as well. So to see how the ball spins and the roughness on it, how that affects the forces on the ball, we're looking at this paper called The Combined Influence of Spin and Roughness Frequency on Sphere Aerodynamics. It's open access, so you can find the link below. And the DOI is at the top left of the page. Now, one final question we need to understand is why spin and roughness might have an effect on the ball's aerodynamics. Well, they're actually related here in that if the roughness drops, then the ball surface becomes smoother, and that means that there is less geometry to bite into the air. So the air around the ball won't be affected as much. As the roughness increases though, there is more to bite into the air, and that then increases how much the air is affected. On top of that, the roughness itself impacts where the flow over the ball will separate. So in figure 2, we see the wake from the ball. The flow separates around the midpoint on top and underneath the ball. These separation points are affected by the surface roughness because of something called the boundary layer. So looking at figure 3, we see different amounts of simulated roughnesses. So these little balls here. So let's concentrate on the leftmost figure first. You can see that each one of these little dots stick up into the air. The size of these dots start to approximate the type of surface roughness you get on baseballs, for example, so they're about comparable to it. As the air flows over each one, it gets churned up. That's important because the flow closest to the surface is very slow-moving fluid. But by churning the fluid up, you mix the higher speed fluid away from it, closer to the surface. It then gives this flow closer to the surface more energy to stay attached to the ball. What that does is change the wake of the ball and the forces on the ball. So these dots should definitely change the aerodynamics of these balls. And we'll cover later on how that happens. What's more, the different spin rates also tell us how much these dots will churn up the flow too. That's because the faster the spin is, the more these dots are going to be churning through the air. Now, the authors have quantified how much of each ball's surface is covered in these dots with these macroscopic surface roughness things. And the way they did this was calculate the percentage of the surface area covered by them compared to the overall surface area. So for the first ball, the one on the left, it was 6.2%. Then the next ball is 12.2%, then 16.5%, then 22.7%. So even the last ball with all these dots, still only about 1/5 to 1/4 of the surface area is covered in them. And we'll see later how increasing the number of dots affected the aerodynamics. So this is the general idea of this research. And just quickly, if you'd like us to simulate your very own car, let us know here. Now let's move on. One really cool thing we see is that in figure 4, these balls are shot out of a cannon. The cannon's power is determined by the air pressure in the chamber as it's released. It then pushes the piston and shoots the ball into the air. And because they're shot out, the balls aren't actually connected to anything. They're literally just allowed to fly through the air as they normally would. That is awesome because that is completely accurate in terms of what happens in real life. The ball can just flow through the air without being attached to anything. Usually, when you test balls and really anything in a wind tunnel, they're attached to something. And when you want to know the drag or lift or anything, any force on the ball, you use a machine like a load cell to then connect to the ball or the object to, and that then measures the force on the object, and then you know. Here, there is no attachment, and that means there's no machine that you can really connect it to. And that's a real strength of this work, that there's no attachment, because that's realistic then, but it's actually a difficulty because then the question arises, well, how do you measure the forces on the ball then? The authors used a very ingenious way in that it's very simple but highly effective and a little bit out of the box compared to regular situations that you test things in. They used basic physics equations to find these properties. So they literally just set up speed traps at regular distances and measured the speed and the height of the ball at different points through its flight. From that, they could then calculate what the drag was on the ball based on its velocity at different speed traps. And from the height of the ball, they could then calculate the lift too. And this is a really clever way and something you don't come across too often. So well done to the authors for coming up with a really good method, an out-of-the-box method, for actually finding the lift and drag on the ball in real life. Now, for all of this setup, the overall uncertainty of the lift and drag coefficients were 4 counts and 14 counts respectively. And honestly, that's really good. That's very impressive based on a fairly ingenious way of measuring the lift and drag and getting the error bars down. I'm really impressed with it. In addition to the drag and lift data, they also took PIV, which is where you shine a laser sheet into the flow and then see how the particles move with time. In figure 6 here, we see an example of the PIV results. Let's now jump to the results to see what the effects of the different levels of roughness and spin are on the aerodynamics. So in figure 7, we see the lift coefficient of the balls at different spin rates. The spin rate is a non-dimensional value and the equation is given in equation 1 up here. Just up here. Okay. That's the spin rate. Now, in effect, the spin rate is the ratio of tangential velocity of the ball at the surface relative to its speed through the air. The different lines correspond in this figure 7 here. The different lines correspond to different roughness frequencies. The solid lines are the data from this work, and the dashed lines are from data from other work. This shows a very interesting trend because where the ball is smooth, so the dashed light blue line, increasing the spin rate generally reduces the lift coefficient, so downforce is created instead. The reason why that's weird is because for the balls with a lot of roughness, so the solid lines and the yellow dashed line, increasing the spin rate increases the lift coefficient, so the exact opposite trend. And looking at the flow viz later, we might be able to get to see why that occurs. But right now, from this graph, it seems like the macroscopic roughness has this effect where increasing the spin rate increases the lift coefficient, and macroscopic roughness, like the smooth ball and the one with very low roughness, the dashed purple lines, have the opposite effect, where increasing the spin rate reduces the lift coefficient generally. So what I think is actually happening here is that the macroscopic surface roughness is tripping the boundary layer to definitely make it more turbulent, while the smooth and not very rough balls still have a transitional boundary layer. That then will change the separation characteristics, but we'll see later on. Another interesting finding here is that these trends seem to plateau, so the spin rate doesn't go high enough to say that for sure, but they seem to start to level off. And I think the reason why it plateaus and doesn't just have this discrete jump where the coefficient just suddenly increases is because the dots aren't continually tripping the boundary layer at the same point at each moment in time. So these results are averages. What that means is that if you look at the overall time, the boundary layer will constantly trip at different locations. Speeding up the spinning means that the boundary layer tripping point will become more consistent at one point. And I think that is the reason why we get these plateaus, because if you look at the tape strip results, so the yellow dashed line, it too plateaus, but it takes longer to happen, it seems. The slope of the line is greater. So I think the same effect is happening here. But the reason why it takes longer to plateau is because the trip strips are not distributed evenly. The trip strips are more discrete, like there are only certain regions which have them, whereas the dots are more randomly located everywhere. So there will be even more transient behavior for this trip strip. Now, another possible effect of the dots are having is that they might be acting like vortex generators. That could also explain why their results plateau quicker with spin rates too, with the high spin rates. So there's a lot going on in this graph and it's deceptively complex, but also maybe the tape strip gave a steeper curve because that data came from a different wind tunnel. Now, after seeing these results, the authors also decided to plot another graph in figure 8 here on the right. It's kind of similar where it plots the lift coefficient, but the x-axis is something a little different. It's a combination of spin rate and roughness frequency. This is kind of an artificial number in that it doesn't reflect any exact flow physics, it is just the equation that will give a linear fit. But the fact that there is a combination of the spin rate and the roughness frequency that gives a linear line here is interesting. And I think that more investigation is needed into the flow physics behind what's going on here. Maybe there is some underlying effect that this regression model managed to capture without really knowing what the actual flow physics is. Now, all of this is for the lift coefficient. What about for the drag coefficient? So in figure 9, we see the effects of the spin rate on the x-axis with the drag coefficient on the y-axis. The different surface roughnesses are shown in the legend. The results here support the idea that these dots create a transient aerodynamic effect. That's because the black line, which is for the roughest ball, has a much shallower line than the green, which is the second roughest ball, and so on as you reduce the roughness down to the blue line. The reason I think that is because the spin rate tells us how fast these balls are spinning. The faster the spin rate, the sooner a dot will rotate into the optimal boundary layer tripping point, where the drag coefficient is lowest. If you have a rougher ball where there are more dots on it, then you don't need to go as high a spin rate to get a dot in the optimal boundary layer tripping point. And what that tells us is that, as you authors indicate, the spin rate and roughness frequency are kind of interchangeable. And this graph shows that the lower the roughness frequency is, the higher spin rate has to be to get similar effects on higher roughness frequencies. But in terms of the actual drag coefficient, lower roughness frequencies are better. They give lower results. But that doesn't necessarily mean that that's what you want. The whole point of having roughness on the ball is to change its aerodynamics. So depending on what you want, whether that's more downforce or more lift, then you might want more roughness, but then there's a trade-off in terms of drag, where there'll be a point maybe where the drag will increase, and while the lift coefficient might increase, the overall lift won't because the ball will travel slower. So as expected, increase in roughness increases the drag coefficient, but also increasing the spin rate also increases the roughness, and that might be a little unexpected here. Let's move on to figure 10 because this shows us the average separation point on the ball at different spin rates. So this is really cool. And these graphs are a little complicated, so let's explain what they mean first. So the ball is spherical. It also rotates in one direction only. Let's say that it rotates forward. That means that the top is rotating towards the oncoming air and the bottom is rotating away. The sides aren't rotating. So really the spin has the greatest direct effect, on the top and bottom. Knowing that, and knowing that these roughness dots affect the boundary layer separation point, what is the effect of spin and these roughness elements on the boundary layer separation around the ball? Not just the top and bottom, but also the sides. Well, in figure 10, we see some information on that. So the top left plot is for the ball with the least amount of dots, and then we progress from left to right, top to bottom, and the bottom right is the ball with the most dots. The colors correspond to the different locations around the ball from 0 degrees to 180 degrees. 180 degrees is the top, which corresponds to the point where that is spinning forwards into the flow, and 0 degrees corresponds to the bottom, which is spinning away from the flow together with it. Then the other degrees represent the locations from the top to the bottom. The first trend that is clear is that as the spin rate increases, the location that the flow separates from becomes more extreme. For example, at the top of the flow, the flow separates further upstream with increasing spin rates, which makes sense because the flow is being decelerated more there. On the contrary, the flow on the bottom separates further down the ball. As expected, the green line, which corresponds to the middle of the ball, so the side, isn't affected much by the spin rate. That makes a lot of sense because it shouldn't be. So these trends make a lot of sense. The side should be affected by this roughness, but the spin rate shouldn't really do too much in terms of that. Another thing that stands out to me is that for when there is only a little bit of surface roughness, so the top left plot, the point on the ball where the flow separates doesn't really change very much with increasing spin, relatively speaking. For example, let's take 180 degrees, which is the purple line. This is the top of the ball. For the different spin rates, the angle around the ball where the flow separates only changes by around 5 degrees, from about 107 to 102 degrees. And when there is a slightly more roughness to it, so the top right plot, the flow angle deviation increases up to about 8 degrees, so from about 105 down to about 97 now. So there is more deviation here. Now, this might be because of uncertainty, which could negate these differences, but even still, these trends hold pretty much for all these lines. So it seems like it's probably not the Aero bars that are making these greater differences in the angles occur. It's actually really a thing. And I think that for some reason, the spin rate really affects how effective the surface roughness is. But then the plot thickens because if we go to the max roughness tested here, so the bottom right plot, the deviation in the angle separation with spin rate now reduces. So I'm not entirely sure why these trends are forming. This last one makes sense because the more roughness you have, the less discrete it effectively is, and so there is less of a transient effect. The effect on the boundary layer becomes pretty consistent. So the first plot's trends are a little bit of a mystery here. Let's now move on from that because in figure 13, we now see the wake area behind the ball versus the spin rate. And that's really cool. So what this shows is that as the spin rate increases, pretty much across the board, the wake area drops. In other words, the wake size becomes smaller with increasing spin rate, and that goes for all surface roughnesses too. But it also shows that here there is more surface roughness. When you have more surface roughness here, the greater the wake becomes too. So the black dots instead of the blue dots, and then the green and red ones. So that indicates that the balls with more surface roughness have more pressure drag too. Now moving on to figure 18, we see the drag of the balls decomposed into the components. So let's scroll down here to 18. And the way the authors decompose drag here is really interesting. First of all, we have the form drag, which is a familiar component of drag. This component of drag is associated with the difference in pressure front and back. That creates a pressure differential that then creates a force backwards, and that is drag. That's all fine. The second component of drag is called the surface roughness element drag, and this is in effect the skin friction drag, and from their description, that's kind of what it seems to be. So that's an easy to understand type of drag too. The third type of drag given here is something called the wake orientation or lift component of drag. Now this one is very interesting. What this effectively means is that when the ball produces lift, the force it produces isn't exactly in the vertical direction. It's actually tilted a little bit, and part of it is in the drag direction too. This is literally like lift-induced drag you get on wings. So I think another term for this would be lift-induced drag, or simply induced drag. And it's cool because for wings, the easiest and probably most common way of thinking about induced drag is wingtip vortices. Here we don't have vortices though. Instead, induced drag can also be explained in several ways, including one way which is tilting the lift vector into the drag direction too. And that is where the drag part comes into play. So it's cool that we get the exact same thing here, just in a slightly different way. Anyway, in figure 18, we see these components of drag making up the total drag. The circles are for the form drag, also known as the pressure drag. The squares are for the roughness drag, so the skin friction drag, and the triangles are for the induced drag. This graph is a little hard to understand, but let's explain what's happening here. So the x-axis is the total drag coefficient. So each drag coefficient is for one ball at one spin rate and with one particular roughness frequency. Then for each of these total drag coefficient values, we have the drag coefficient broken up into these three components of drag. Their values are indicated by the y-axis values. For example, for a total drag coefficient of 0.247, so the lowest one, the three blue dots show that the top, the circle, for the form drag is definitely the highest. It's at around 0.21. So out of the 0.24 value for the total drag coefficient, 0.21 of that is pretty much just the form drag, and that's the vast majority of it. So we can conclude that the total drag of the ball is mostly from the form drag or the pressure drag. From there, only 0.037 is left for the other two components of drag, so 37 counts compared to 247 to begin with. And here, the induced drag and the friction drag are about equal. So for this low drag coefficient, the induced drag and friction drag are pretty minimal. As the total drag coefficient increases, all these components grow by about the same rate. The form drag always remains the most dominant component of drag, while the skin friction drag and induced drags make up just a few counts each. So most of the ball's drag coefficient is mostly from the pressure drag consistently. Skin friction drag is typically about double that of the induced drag. So that's the second most important part, and then the induced drag, which is the least important part. So what all this tells us is that if you want to reduce the overall drag coefficient of the ball, you should focus on reducing the wake size. That will easily reduce the drag by the most compared to the skin friction drag and the induced drag, because there's not nearly as much there to really get out. So even if you were to make a major breakthrough there, you're still only going to gain like a few counts, as opposed to a major breakthrough with form drag. You're going to get like 20 counts, 100 counts. And with that, we come to this podcast. If you liked it, hit the liking and subscribe buttons. And if you want to learn OpenFoam, check out our courses here. And if you want to learn more about surface softness and how that affects golf balls, check out our Aerodynamics podcast here. Peace, amigos.